Okay, let's get it started. It's my pleasure to introduce Yu Sun as our colloquium speaker today. So Yu Sun is a postdoctoral researcher at Stanford and a research scientist at NVIDIA. He's working with some of our really good friends who we know some of them, including Carlos Gestrin. So today, you will talk about some of his work on test time training. So in fact, we know he's one of the first people who's started this topic called test time training, and I've just learned you guys coined the term. He's done this during his PhD in building these models for computer vision applications, and most recently extending it to many other domains like scientific discovery, coding, and more. And he started this in 2019, and since then, it has become very popular because it kind of resembles the way that humans learn. So very excited to learn about this. Thank you.
Oh, thank you for the introduction, Hannah. Let me begin. Okay, so a little bit about myself. So I grew up in the Shandong province of China. That's this thing over here. It looks like a rotated like button. It's the hometown of Confucius. He's a famous Chinese philosopher and pedagogue. And perhaps for that reason, our province is very serious about tests or exams. Okay, and in fact, it is so serious that when we have exams, we have armed police guarding the exams shipped over here in those crates being transported, and because how carefully we guard these things, right? The process of studying often becomes a constant process of guessing the test problem. So when American kids are guessing about betting on baseball games, we are betting on what exam problem is going to show up in the next test. And the process of testing is really praying. As I'm going through my test printout, I'm always praying, that that's the next one. Oh, it's got to be something similar to what I have studied, because otherwise I don't know what to do about it, right? And then I came to America when I was 13, and I discovered a great thing in America. It's called take-home tests. And the great thing about take-home tests is that you can learn the relevant content while taking the test. So there is really no guesswork, right? Now, just to give you an example, when I was taking machine learning theory, actually the take-home test was given to me during the first week of class. I just have to solve, a list of problems up to 10 stars. And in fact, one among the list was this open problem in learning theory. And if I just did this single problem, I could have gotten an A+ in the course. I could have done that in the first week of class. That was the spirit of American take-home tests. And now you ask, why would America survive this, right? Like, something like this. I mean, in America, we call it take-home test, but in China, it's called cheating. Why do you survive this? Well, it's really because that tests, at least good ones, should be a proxy of the real world. And in the real world, we end up learning on the job all the time. And that's perhaps speaking a language. When I first came here, I wasn't so good. Now, after just years and years of practice on the job, I'm better. And think about driving, or perhaps the ultimate form, doing research, right? So when you do research, you always are learning on the job about your research problem. And here's, an extreme case. So this gentleman, Andrew Wiles, he spent 9 years proving Fermat's last theorem, right, and succeeded. Now, when he was 10 years old, that's when he first learned about this problem and decided to be a mathematician. And then, after he became a professor, he decided to work on this problem in complete isolation He did that for the next 7 years, and then for 2 more years, he ended up proving the problem. And this is sort of the big take-home test of his life, right? Which he did well on. Now let's think about how testing works in machine learning. So when this project started in 2019, machine learning has 3 stages already. So we do pre-training on internet scale, right, general knowledge, fine-tuning on some specific domain, and then comes testing, where you fix your model, right, and it just gets deployed. It's sort of the most boring stage. Today, fine-tuning is now called post-training, but not much else has changed besides the dramatic difference in scale. Right? Conceptually, it's the same thing. Specifically, the process of post-training is always about guessing the test instance. And the process of testing, you're just passively praying, right, that whatever test instance you see, it's got to be something you've seen similar to what you have post-trained on. It's the same thing. And this is the case because really most of machine learning was happening before you see the test instance. The moment when the test instance arrives, right, is really a defining moment in machine learning. And after this test instance arrives, well, you're just passively testing there, not much interesting happening. And I believe that in the future, most of machine learning will be happening in this part, okay, at that side of the boundary. Now you might be thinking, how could it happen in this part? At testing your model is fixed. Well, the whole point is that we should be training the model at test time, and that's what this talk will be about. So let's zoom into this future, okay? And the simple setting is when you have a test problem, such as this problem in machine learning theory, and then you're also given a pile of lecture notes, right, as data. It's data given to you at test time. And here, right, the most fundamental problem, and here, because the test problem, we think that it will be solved once you understand the relevant data. So in this setting, the fundamental problem is how to efficiently process a lot of data, right, given at test time. That's a simple setting. Now you might think, what's the hard setting? Well, that's when you're not given the data anymore. And this could happen, right, because maybe your test problem is just an open problem. There is no lecture notes that would enable you to solve this problem, right? So that's what Andrew Wiles was doing, in his research. And because he could do it, we thought maybe we could formalize this process and take a crack. So that's the outline for the talk today. We'll go through the simple setting and the hard setting, just those 2 things. All right. Now let's zoom into the simple setting, okay? And just as a reminder, you're given the data, and in addition to the test problem, which is solvable once you understand the data. So here the focus is on the data, right? How to efficiently process a lot of data given to you at test time. Now, data given at test time, in machine learning, we have a special word for it. It's called context. And if you have a lot of it, we call it long context. Okay? That's a long context problem. And people say this is among the most economically valuable problems today because people want to give their language models, large legal cases, entire code bases, and long histories of interactions. So, all the frontier labs, they have dedicated teams working on this problem. Yet, people also say it's one of the biggest bottlenecks in AI today. Right? Now, how does this become a bottleneck? Because after all, when you have data at training time, you know how to deal with it. You just do gradient descent on the model. Right? You know how to deal with a lot of data given at training time. Now, how come that at test time, when you give it a different name, you just all of a sudden don't know how to deal with it? Well, it's really because that at test time, at least in the old days of machine learning, people weren't comfortable changing the weights of the model. So you have to come up with workarounds to use data without changing the weights of the model. And the most popular workaround is called self-attention. That's the key component to transformers. Okay? So just a little bit about how self-attention works. So in transformers, using self-attention, right, you want to store the embeddings of every word in a growing list because that's how you will use the data, how you will use the words in the data. And this list is usually called the KV cache. So here's an example. Let's say this is your data given at test time, your context, right? And you want to process each of them into an embedding. So suppose I have already processed 2 of those words. And now, for the third one, I first do an initial projection into an embedding, but now I want to incorporate the information, right, of the words before it. So how do I do that? Well, I just compare these embeddings, right, with this word, and then collect all the information that I get from these comparisons. So this process takes 3 units of compute in this example. Now, the important thing is that for the next embedding, right, this same process will take 4 units of compute, and the next one 5 units of compute. Right? So the key idea is that now the cost per word grows linearly with longer context. Right? So you can see this with those empirical measurements here, right? That as context length grows longer, the latency, which is the cost per word, right, is growing. So your model gets slower and slower for each word as it's going through your context. And this is how long context becomes a bottleneck. So people come up with more workarounds on top of this workaround. And this one is called sliding window. Right? So the main idea, very simple, is what if we only, right, keep tab of the most recent words, right, instead of all the words. So now, let's say the most recent 3 words. So now I only cost 3 units of compute, right, a constant amount, no matter how long my context is. And as you can see in the empirical measurements here, right, the line is flat if you have sliding window, but this comes as a cost. You will forget the tokens that are outside of your window. Right? So let me help you, understand this plot. It's a very important plot. So as you have longer and longer context, right, I'm measuring the language modeling loss. And in order to clearly show the trend, I'm benchmarking the loss of everyone against that of the orange line. Right? So I'm subtracting the orange line from everybody. That's why the orange line itself is now becoming 0, right? A flat line is 0. And now you can clearly see the trend that the green line is rising steadily compared to the orange line. Right? So sliding window gets worse loss in longer context compared to transformers. Not surprising. That's the price you pay for only using the most recent tokens. And the holy grail in long context language modeling, if you want to scale this context length, right, is to be flat in both panels. So a lot of people have tried. This has been an area with a lot of research. And I'm just picking 2 representative examples here. So one is Mamba, and the other is called gated delta net. So you can see that both of them get better offset compared to sliding window, but pretty much the same scaling, right? So how would we solve this problem? Now, let's just zoom back for a moment and think about how this problem showed up in the first place. So it happened in the first place because, at test time, when you have data or context, right, people aren't comfortable with just changing the weights of the model. I mean, we aren't comfortable with just taking the approach at this side of the boundary and doing it over here, right? So what if you just do that? You just forget about the boundary and use the same approach. And that was the main idea of my paper back in 2024. And since then, they're having a lot of direct follow-ups. And this line work has heavily influenced the modern revival of continual learning. And today I will talk about my most recent work, which is really the simplest of all. So suppose we have a long sequence of words. That's your context. And you only want to use a transformer with sliding window. That's the green thing, which is supposed to have constant latency across time. Okay? And now you not only do a forward pass for this model, you also do a backward pass, right? Using the next token prediction loss, which is just the same loss as you use during pre-training. And this enables you to compress the content inside this window into the weights of this model, right, as is moving outside of that window. So right now, while the model could only attend, right, to the context that's immediately below it, the context before it has been compressed into the weights of the model. And over here, you do the same thing, and so on and so forth. It's very easy, right? So after all these steps of gradient descent, when your model is finally over here, even though most of the context is outside of this window, right, they should have been, the information in that context should have been in the weights of the model because you were doing backprop, to update those weights. That's the main idea. And contrast this with just a transformer with self-attention over the entire context window, over the entire sequence, which is just going to do a giant arrow of forward pass. And the question is, are all these little arrows combined going to be faster than this one big forward arrow? And are they going to be as effective, right? Are they going to compress the content outside of the window, as I said? So for this, let's look at the results. So just as a reminder, right, the holy grail here is to be flat in both of these panels, right? And here you want to have constant latency, and over here you want to have the same loss as transformers across context lengths. First of all, for latency, well, this is how our method does. So it is indeed slower than sliding window, because you have to pay the cost, right, of test time training. You have to do the backward pass. So that's indeed slower. But at around 32,000 and afterwards, that's when it is actually faster, right, than the giant arrow, the giant forward arrow of a transformer that's attending to the entire context. And that's for prefill. At 128K is 2.7 times faster in prefill, and it will be 6 times faster for decode. So in order to make it work for this side of the plot, there are some important details, right? So I was using the analogy of testing and take-home tests. Right? So in regular machine learning, as I was saying, at test time, we want to do well, right, on these tests. So training is like doing practice tests. Now, I have just changed, right, the process of testing to the analogy of take-home tests because we're doing test time training, right? But take-home tests, doing well on take-home tests is sort of its own kind of skill, right? And that skill can be pretty different from doing well just on regular practice, just on regular tests. So if you just practice regular tests during training, you're practicing the wrong skill, right? So in order to practice the right skill, you want to also do practice take-home tests, which in the language of machine learning, we call it learning to learn, also called meta-learning. So this is an important detail that we need to take care of. And once you do that, you see that our method here is indeed flat compared to transformers. In fact, it has a constant advantage. Okay, so this gap means that it's doing better than transformers for all context lengths. And this is the first method with this sort of scaling behavior, to the best of my knowledge. So if you put back all the other methods that have constant latency, you see that, because of the different scaling on that panel of the plot, there is a big difference for 128,000 context. Yes?
What exactly are you doing under the heading of meta learning?
Under the heading of?
Meta learning.
Of meta learning. Yeah. So the most naive approach is to say, okay, so I'm going to take each training sequence, do gradient steps on it, go through the entire sequence, which could be a lot of gradient steps, right? And collect the language modeling loss over this sequence. Now, that loss, right, is exactly the loss you care about. So during training time, you could backprop through that loss. And because the process of generating that loss already includes taking gradient steps, the process of backpropping through that loss would mean that you need to take gradients of gradients. Right? So concretely, this optimization would involve gradients of gradients. Now, this could be slow. So there are good first-order approximations to these gradients. Namely, you don't actually need to do them, but that's a good, conceptual way to think about it. Did I answer your question?
Let me ask the question another way. What goes wrong if you just do backprop at test time?
And at training time, you don't modify any of the pre-training algorithm, right?
No, you have your model, and then you have your test time data, and you just do backprop as before. That's the easiest. What goes wrong?
Yeah, so that is what we do. The only thing that we change in that important detail part is how we prepare for test time training, is what we do before test time, at regular training time. Did I make sense?
I understand, but I'll ask you more about it.
Sounds good. Okay. Any other question? This is a good point to be asking questions. This finishes the first little part of my talk. Yes, please.
How large is the context window for your method?
Yeah, so it's 8,000.
Okay.
That's why you see that, we're just taking the green line, right, basically. We're taking the green line as a baseline and doing test time training on top of that. So that's why you see that the green line and the orange line are the same over here.
I see. And have you experimented with making it smaller and seeing how small it can go before you get higher loss? Because it seems like it's a different kind of assimilation of context.
Yeah, we have done smaller, but it's not quite that interesting, I feel, because smaller, you don't go much faster. And basically, 8,000, it saturates the hardware. And if it's 4,000, you don't get much of a speed up.
Right.
Yeah.
I just wonder if you can make it very short and have
I have gone down to 0 actually, depending on how you think about it. Basically, the limiting version, right, would just be you don't have attention at all. Right? It's like a bigram. If it tell you, if you say something like, Stanford University, it's going to work because it will see Stanford and predict university. It's a two-word association. If you give it University of Washington, it will see of and not know what to say next because it's not a two-word association, right? I've tried it with that model. Yeah, for that model, the improvement of doing test time training is of course dramatic, but you will lose some performance compared to the transformer with self-attention. And I feel that loss is rather unnecessary because that model isn't so much faster actually. Yes.
Yeah, on the other hand, what happens if I don't care about runtime? If I just take a really large context and then use meta learning, do I get substantially better loss performance?
So you are saying that you take say orange line,
Yeah.
and do test time training on top of that,
Yeah.
yes, you get better performance.
How much better?
It is better than, it is going to be better than the blue line, but not quite, not a huge, it's something, I believe it will be something like, so this is something like 0.02 or 0.016 or something. It will probably like double this advantage. It is in the paper. Yeah, it is an experiment in the paper. Just check out the paper. Anything else? All right. If not, yes, please.
How are you evaluating loss here during like inference time?
So it is just language modeling loss, right? So how do you normally evaluate language modeling loss?
It's still next token prediction.
That's right.
Like if you're interacting with a chatbot and you wanted to learn the context of your conversation, like what is the okay, I think I see what the loss means.
All right, sounds good. Okay, if there's no more questions, then I will go on. Let me go on then. Cool. So I have covered the simple setting. Right? Now, what about the hard setting? That's when you're not given the data, right? And how do you do that? So just to say it in a different way, right? In the simple setting, your test instance is solvable once you have learned from the context, right? But in the hard setting, you're not given this bridge. So how do you build a bridge of that sort? And in machine learning, this can come up, by the way, when your test instance is an open research problem. And in machine learning, our abstraction for this is called outer distribution generalization. So that's when your test instance is not represented by the training data. So back in 2018, when this line of research first started, I was studying this problem in the context of object recognition. So say you have ImageNet over here, and you train on that, but you want to run your model on a snowy day. Right? And you have never seen a snowy day in your training set. What do you do? Right? So first you notice that if you are to train on regular ImageNet and test on a snowy day, of course, there is a dramatic performance drop, even for the state-of-the-art models. And if you train and test both on a snowy day, right? If you were able to do that to eliminate the distribution shift, yeah, then there's no drop. Right? It's a distribution shift that's causing the trouble. So wouldn't it be great if we had training data on a snowy day? Right? Well, in fact, we do. It is just on this side of the boundary, right? And it is the very test instance itself that can serve as a piece of training data on a snowy day. You just need to be willing to train on it. So the central difficulty is that this test input doesn't come up with a label. That's why it's called a test input. So how to generate data from an unlabeled input for test time training? That was a difficult question back then. It still is today. Right. So back then, my answer was to use self-supervised learning. Let's see what that means. So say you're doing object recognition, and you have this neural network, and it's giving the wrong prediction. Right? Because it's deep learning, this sort of prediction is usually wrong because the network has bad intermediate features. That's what will break deep learning. And self-supervised learning is a way to fix the features with only unlabeled input. Exactly what we want. So let me explain it using an example, and let me make some space over here. So this example is called masked reconstruction. Right? So you have this image, and you can just apply a random mask to it and ask the neural network to reconstruct it. For that task to type check, you have to give it a different head. Right? That's the reconstruction head. And that's going to be different from the main task head up there. Right? But as you try to reconstruct this image, it will ask the neural network to form, it will have to, form good intermediate global representations for the image in order to fill in the masked parts. Right? So the process of training is just to learn how to better reconstruct by comparing the original image to the reconstructed one. And you keep doing this, right? You keep doing this comparison. And in the end of training, once you're able to reconstruct the image fine, you would have learned the good features. So now you're ready to put back the main task head. And you make a prediction, and if it doesn't succeed, you just repeat this process again with a different random mask. So this was the result we got back in 2019. As you take more gradient steps at test time, on the self-supervised task, you are getting better accuracy on the main task. Right? So the gains between those two tasks transfer, and the self-supervised task doesn't need the label. That's it. So this was one of the earliest cases of test time compute working in deep learning. And you might ask, this is interesting, but it's only for object recognition. How could this idea still be relevant for hard problems today in science and engineering? Well, so let's think about how humans really solve hard problems with only an unlabeled input. Here's an experience you can all relate to, perhaps. Think about your first really hard programming assignment. Right? And this assignment is really hard because you've gone to the lectures, done the homework, but it's just so much harder than what you have seen over there. So how would you do it, right? You at least need to try. You try, but you will stumble and fail. But maybe you will, the autograder will show you a little sign of life, right? You've passed one test case or something. You have a little partial success signal. And once you have all these search trajectories, right, the important thing is you want to internalize this experience. So you can generalize a bit further than them in your new search trajectories. And in AI terms, the first is just called search, and the second is called learning. So when people do it in AI, we have pre-training and post-training, and prior work even do search at test time by prompting the LLM to attempt the problem, and more sophisticated search strategies. One of them is called AlphaEvolve. So the key idea of our work, right, is to just train on this new experience from a single problem. Now, this new experience is the most valuable experience, right, because it is specific to this problem. So it is exactly what you need, to bridge the distribution shift from over there to this particular direction. Right? And let me give you an example to illustrate how it works. So this is in GPU kernel engineering. Say you're given a test problem in PyTorch, right? And that's what you tell the LM, now write me a fast CUDA kernel implementation of this piece of PyTorch code. And the reward in this case would then be the runtime of the inverse reward would be the runtime of the kernel. Right? You want it to run quickly. And I will show you actual data recorded during our run, our test time training run, in a competition called GPU mode. You can think of it as sort of the Kaggle of kernel engineering. Right? And I will show the reward distribution over here, and our goalpost is to exceed the best human. So this is a result from prior work. So if you do search, say you sample 25,000 solutions from this LM, right, with parameter theta 0, you get that reward distribution over there. And this line over here shows what's the best solution if you just do search. Okay. Now our idea is to break this search budget into 50 rounds of search, each round with an improved model. So we'll still have the same total budget, right? Just, well, the first round, we're only going to use 1/50th of the budget with the initial model. So that's why you see the reward distribution is just a little bit squishy inside, right? Because we have a smaller search. And you get theta 1, right? That's the improved model, using the search trajectories you just generated. And you do that by learning on the solutions reweighted by their rewards. So this is going to reinforce the good solutions and penalize the bad ones. Right? Doing this will reinforce the good solutions and penalize the bad ones. And this is a form of reinforcement learning, just carried out at test time. Yes, please.
I thought the problem here was that at test time, you don't have the solution, so you have to learn from partial results.
Yes.
So what is the signal? What is the reward signal in the partial results that you're using?
Yes. So in this particular case, right, a partial result would be a kernel written by the LM. It is still a valid kernel, but its runtime would not be very good. It will be significantly worse than the best human, such as this runtime over here. Right? That makes it a partial result, and the runtime itself serves as the reward signal.
And in general, you would have to find something like this case by case?
In general, the LM would be able to find this sort of a reward when the problem definition naturally induces it. But there are, of course, problem definitions that do not induce such kind of reward. Like if you're trying to prove P not equal to NP, for example, you're not going to get that, right? Okay, so yes, please.
Is it fair to assume that you would be able to do this type of test time training if the solution is verifiable?
If the solution is not only verifiable, but also has continuous reward. So P not equal to NP is it's if you use a formal language verifier, you can verify it, but the reward is pass or fail. Yeah. So I think the best intuition for where the algorithm would apply is that any metric where you see humans hill climbing on, this is a natural thing to apply. Yes, please.
So you said continuous. Does it matter whether or not it's actually smooth or you have a gradient here? Say for
the gradient does not matter. When I said continuous, I just meant that there's a wide range of such rewards, and this range is actually meaningful in the sense that if you keep improving in this range, I mean, it's sort of like just think problems where humans can hill climb.
Okay, I was just trying to get a sense because if there's 10 values that are ordered, that's continuous from your perspective.
Yeah, so if there's only 10 values, right, then you run into the possibility that you might just get stuck at value 5, let's say. Like if you search for a big budget at value 5 and everything still returns value 5, you're stuck, right? Like the key to making an improvement is that when you search, there needs to be a spread of the values. Cool.
Thanks.
Yeah, thanks for the question. Yes?
Is there an analogous reward signal for the case where you're just talking to a chatbot and you expect them to remember previous context, for example? Because it seems like that's sort of the use case of continual learning.
I think it's a limited use case of continual learning. And in that case, I think a reward signal is just how well you are at predicting the next token. Right.
The human's next token.
I mean, if you're trying to read, let's say, a book that a human is giving you, then it's the same as trying to do what we call prefill, right? So if you're trying to prefill this book, you're trying to read this book, yeah, one natural reward signal as you read this book is how well you are able to, predict the next token. And this is indeed the reward signal that we've been using for the previous project. Just because this reward is fully differentiable as a process of predicting this is fully differentiable, we don't need to do reinforcement learning. Yeah, it's a nice connection that you drew. Yeah, any other question? Cool. Then let me go on. So I was just talking about how you go from search, right, getting a range of trajectories with different reward values, going from that, right, to learning. That is just penalizing, learning to reinforcing the good solutions and penalizing the bad ones. And basically you just keep repeating those steps, right? So if you do that, and we inspect all the kernels, we inspect, and we also have the competition organizers inspect all the kernels that we have generated. So you see that theta 10, it learns to consistently apply mixed precision to this particular problem, and you keep going, you see some other ideas that the LLM is able to implement, and finally you will get a solution. You will get a solution here that beats the best human. That's it. Now you see that the distributions are getting wider here. Right? So this is an important detail that is particular to test time training. So in classic RL, right, you want to produce a model that produces good solutions on average. Namely, you want to optimize for this quantity. That's just the average reward of the actions drawn from your model. Now, this means that once you have a good solution, in order to make all solutions pretty good, right, or the average solutions pretty good, you want to sort of collapse to it. Then the bad solutions before would become this good one, and your solution is you have higher reward on average. Now, our RL problem is somewhat special. Right? We only care about one amazing solution to this problem. In fact, we don't really care about the policy. It is nothing but a means to an end, right? Like our goal is just to get a solution, and if I sample 500 solutions from the policy and 499 of them are crap, I don't care about them, right? As long as there's one that's amazing. So the way to say it in math is just if you sample 500, all you care about is the performance, right, of the best of them. That's it. So we really have sort of the extreme case, right, of an exploration problem. And exploration is a long-standing problem in RL. There are many strategies to deal with it. But in our case, because it is so important, right, I think the most principled way is just to bake it into the objective function and optimize this thing, literally. Now, the max is hard to optimize. So we can just do a softmax instead with log sum exponential. It's a standard trick in machine learning to implement a softened version of the max operator. And that's what we do. Right? So after we take care of this detail, our algorithm discovers a new best solution for every problem that we have attempted in kernel engineering, mathematics, algorithm design, biology. And we had all the new solutions reviewed by the organizers or domain experts. So here, yes, please.
What did you use to generate the multiple solutions?
So you have an LM, and you prompt it with the original problem. And if you are building this on top of a slightly more sophisticated search strategy, you would also prompt it with perhaps some solutions that it has seen before.
So you vary the prompts?
Across each round, yes.
But do you do that in an automated fashion? How do you generate them?
In an automated fashion.
Yeah, but how?
So you are saying the prompt to, okay. So the prompt template, right, is just taken from prior work. So there are prior work that's doing this. For example, this Erdős problem. I was just showing how they have a search baseline. So we just take the same prompt template.
But, yeah, sorry, but that's one template. Where did the variations come from? Are they random or?
They are random. Yeah. The variations are random. Right? You fill in the template with a problem, and then the variations will come from some randomly sampled solutions from your past rounds. That's it. It is really simple, actually. This way of doing it. So this is a math problem. It's a problem in combinatorial number theory. It's called the Erdős minimum overlap problem, and people are trying to improve this upper bound by making it lower. Right? So lower is better, and that was a previous human result, and DeepMind improved on this with their thing called AlphaEvolve, and that was the best search baseline. So a few months ago, Terry Tao collaborated with DeepMind, and the latest version of AlphaEvolve, and improved it further, right? So if you just run an open model on this problem, it's not going to do very well. But if you do test time training, it improves the result dramatically. Right? It's a huge margin compared to what they were able to do before. Yes, there are questions. Yes, please.
Did we learn anything about the problem from the 3 bars on the right of this?
Yeah. So I did not learn anything. But that was my problem, I would say. So we had math professors review our solution, and I think if you read the reviews in our paper, right? So their center point was that actually all the solutions that the previous things have found are symmetric. So to illustrate what that means, we're trying to find a step function that's a constructive upper bound, right, for these things they are doing. And basically, the functions they found are symmetric, and they say our thing is asymmetric. Hopefully they learned something, if that makes sense.
Okay.
I mean, it's hard for me to learn something from it. Yes?
Is there, for these math problems, did you try it with just one open model or across a range of smaller models also? And were the smaller
we tried quite a lot of smaller models, yes.
Were they able to improve upon it or have a good solution?
Yeah, I think this was, I think we even had Quinn 8b. And I'm not sure whether it was, I need to check the paper, whether it was improving upon this gray thing. But it was definitely improving upon the green thing. Right? And if you ask whether TDT was improving the small model without TDT, yes, then by a huge margin. Yes. Yes, please.
Is there a specific RL algorithm that you use? Is this policy optimization or?
Yeah, so a big difference between the RL algorithms, right, is just how they sort of constrain the update. Usually for PPO stuff, you do this KL thing kind of constraint. So we still keep that. And then the most important is how do you get, how do you go from the raw rewards of this sort, right, to the actual weights of the solutions. So, what I showed here, right, using this objective would just give you a different way, right, to weigh the solutions. And that's called the entropic utility. So you can think of us as doing a combination of RL techniques. That yes, so yeah.
And how sample efficient was it? How many times did you have to prompt and get a reward on each?
Yeah. So really, in this example, each in time index, right? Going from theta 1 to theta 2 means 1/50th of the search budget, which is our total budget was 25,000, I believe. And yeah, it was 25,000. So 1/50 of that is 500. That's right, 500. Yes, yes.
Actually, can we take questions later? We have 5 more minutes.
Okay, let me, sorry about this. Now I'm basically out of time, so so let me wrap up. So, okay, this is what we talked about today, right? That the moment when the test instance arrives is really a defining moment in machine learning. And most of machine learning in the past, pre-training, post-training, mid-training, all these things, they just, they were about, what to do before the test instance arrives. Okay, and I think the future is about what to do after the test instance arrives, because then you no longer need to guess what the test instance is. And I talked about the simple setting that's, given the relevant data, also known as context. So I showed this pair of plots, which was, the first result, to the best of my knowledge, that's scaling with long context in both panels. And what I didn't get to show are, that we applied this technique to generate, 1 minute long videos packed with a lot of, dynamic motion. And you can do this just by giving the model one long plot in text, a big storyboard. And it just generates the entire video in one shot with no human editing. Right? So this was the first model that was able to do that back in early 2025. And long context, right, is only the easiest form of test time training. Yeah, let me go on then from the video. So now I also talked about the hard setting, and there is no relevant data, right? And in the hard setting, I talked about how to generate data through self-supervision and discovering state-of-the-art results for scientific problems. What I did not get to talk about are all the work I did in robotics, including manipulation, locomotion, and for perception. And I will probably come back to robotics sometime in the future. Now, the most important things that I didn't get to talk about are the hundreds of direct follow-ups from other people since my paper in 2019. And just to give you an example, so Alpha Proof was the first paper that was able to win an IMO medal, and they say that for peak performance in their most complex problems, test time training is crucial. So they just prompt the LLM to generate some easier exercises of the test problem that they actually have to solve. And this technique is also applied in the leading math theorem proving system today. That's called Aristotle biharmonic. And they also did a lot of experiments on test time training in their write-up. So there have been many methods, under the concept of test time training, and most attribute my 2019 paper for bringing this concept to deep learning. I think of this as my most important contribution. So in the future, right, I believe that the hard setting with no relevant data is going to be the most powerful application of test time training. And specifically, I like to solve problems, start with verifiable problems with no continuous reward, right? Such as proving hard math theorems. Because after all, that's what Andrew Wiles was able to do in those 7 years. He was practically working in isolation, just studying this problem, and can we formalize this process? Right? So I like to start with verifiable problems without dense reward, such as proving P not equal to NP. And then this is actually only the easier among the hard problems. Right? The harder among the hard problems would involve interactions with the real world, such as robotics and when you're interacting with real users. Now, in the end, I believe that AI can be the Andrew Wiles of the world's hardest and most important problems. That's all my talk. Thank you.
We have time for a couple more questions. Maybe we first start to.
Sure, yeah. That was a great talk.
Thank you.
Should I get the mic?
No, they said
Okay.
no.
I guess the question was regarding like the RL algorithm you were describing. You know, I'm more familiar with just traditional RL, but you know that has some features of like reward-weighted regression or that type of algorithm. And I guess the question is more like, have you like how similar is it to that? But also like, is there much to learn from like the like reward the RL methods used for like more standard RL that can be applied to this as well?
Yes. So, so let me answer this question, both in terms of what's being done now, and in terms of what will happen in the next maybe 2 to 3 years. So in terms of what's being done now, here's how I try to do this research, right? Is I try to do single problem RL at test time. That's my main idea. And for the rest of the research, I try to use as much of the default RL techniques as possible, right? So people would be able to focus on the main difference in isolation, right? So in this context, I mean, we basically try to borrow most of the traditional RL techniques. Even the entropic, utility, it has appeared in traditional RL. It just didn't matter that much in that context. Over here, it matters a lot, right? Now, going on, I believe this sort of scenario will become more important, this sort of borrowing. Like, traditional RL thinks about sparse reward, right? Sparse reward meaning, like, you try the problem a lot of times, you don't get much reward. That happens in traditional RL. Now, when you do test time training, it is a lot more extreme. When you have a binary reward problem, such as proving P not equal to NP, that is the most extreme. And the techniques that people have developed in traditional RL for this sort of problem, one is called hindsight experience replay. That's something I've been trying right now. Well, it's going to become more important in this scenario, and we might need to make it more extreme. So that's sort of the relationship I see, both in terms of past project and in the future.
Thank you.
So one more question.
So everything you covered in this talk is there's one test example.
Yes.
But in continual learning, you have an endless stream of examples, every one of which is both training and test is in humans.
Yes.
How would you do things there? Just treat this one at a time? That seems like missing some opportunities.
Yes, absolutely. So in fact, right, while I was talking about the simple setting, where you have long context, you are already training the model online, window by window, right, in a long sequence, and that will be a good idea in the future if you have a lot of test problems that are highly related, right? And the biggest benefit for this is that you will be able to save compute, because the compute that you have spent for test time training on an earlier problem could be used for a later problem if they are highly relevant to each other.
So in that case, isn't it like unsupervised learning setting, right? Because you have a model trained, then it's like another stage of training with just a group of examples without labels.
Yeah, and the key idea, right, is that each of these examples is actually a test instance, right? Is actually where you get evaluated. It is the purpose of training on that test example is not only to prepare for future ones. It's not to generalize to the other ones, but to do well in itself. Helping the future ones is only a byproduct of that.
Okay. Thank you very much. Amazing talk. Thank you.
Thank you, everyone. Thank you.